Greetings and welcome once again. I'm John Gabriel. So in the previous video we talked about an arithmetic mean extensively, and we said that it only makes sense if and only if redistribution makes sense. And let me just turn off dark mode because most of you are not as blind as I am. So let's do this and continue. So we also went into a little bit of the recommended new word for arithmetic mean based on the two adjectives flat and equal, which were correct in only one human language, and that's Chinese, which defines the level magnitude as flat and equal in Chinese as ping jun. Okay, and we saw that in Dutch it was plat, lake, and Hebrew it was château, just a combination of these two Hebrew words here. In Greek, epipediso. In Spanish, plano igual, a combination of these verbs here, and I don't know what I did here, but I think I should have done that right. Yeah, okay. And also in German, and of course you can do this in any other language and have a new word for arithmetic mean instead of arithmetic mean, which is wrong, by the way, because first of all, the level magnitude has nothing to do with the middle of anything, and it has nothing to do with relative position. Okay, neither of those things, so it's a complete misnomer. And of course, the stupid modern Greeks totally missed that, and they called it in Greek Arithmetikos, Mésos, όρος, which means arithmetic middle term. Totally wrong. Okay, and to read more about that, you can see this article here. Okay, the ancient Greeks did not define arithmetic mean and may have not known of it. Of course, the plain number is really a product of two arithmetic means, but that's not what it says. All right, so now, how does this all tie into calculus? So you'll remember that during the video I showed you a picture where I told you that, let me just come over here, where I told you that all these vertical line lengths, we find their level magnitude. And how do we do that? We do that through the mean value theorem. In one step, it's just a difference of the primitive function, isn't it? So how does that work? Okay, so let's go to the Holy Grail article on academia.edu. I'll place links to all of these again so that you can look over them. This is a very powerful identity. Okay, it doesn't come, it's never been printed anywhere in mainstream, and the only parts something similar has been done is in Labar, but not in this context. It's done in the context of limits and the Lipschitz condition. Total bullshit, irrelevant bullshit. Has nothing to do with slopes and nothing to do with connecting the derivative to the integral, as I do in this identity here. And then the other place, the most recent attack is that crap on Wikipedia called the fundamental increment theorem, lemma. It's just a joke, by the way. It's not even a lemma. It's a laughable little article written by some idiot. Okay, and it's nothing compared to this. It doesn't say anything like my article does and like my historic geometric identity does. And my historic geometric identity was realized from the new calculus. So how did that work? Well, let me show you very quickly. So in the new calculus, let's get a pen. Where's the pen? No, I didn't do that right, did I? Oh gosh, get out of here, man. Pen, there we go. So in the new calculus, the derivative is defined like this. And of course, it's a little more difficult in the beginning, but it's 100% solid, something which you can't say about the bullshit mainstream calculus. Okay, that's equal to f prime of x, and you can say it's also equal to f prime of x plus q of x mn. Now, what do these things mean? Okay, so this is what it means. It means if you have a function like this, let's call it f, and you have a tangent line here like that, and let's say it touches at the point x. Now, any parallel tangent, and by the way, there are infinitely many, so to speak, because Euclid proved that over 2,300 years ago. If you have a point there, you can draw a line parallel through that point to the tangent, okay? So it's parallel. And M and N, you don't get to choose them like the bullshit that you do in your mainstream calculus with epsilon delta. There are no games here. All this is very carefully thought out. This distance here is M. This distance here is N. And these here are all related in the auxiliary equation. Now, you don't have an analog in the historic geometric theorem. So the historic geometric theorem says f of x plus h minus f of x over h is equal to f prime of x plus q of xh. Okay, so q of xh is never, it's unlike the new calculus, which is always equal to 0, and this is an auxiliary equation for which there are many powerful uses. I'm not going to talk about them now because I could write 3 books on it. And in the historic geometric theorem, this here is never anything but the slope difference, okay? So in mainstream calculus, you've got the tangent line there, and you've got a non-parallel line like that, and you just constantly get closer to the tangent line, right? So in my historic geometric theorem, f prime of x is the slope of the tangent line, and q of x comma h is the difference between the tangent line and the secant line, as you see explained in this article. Okay, so I'll put a link to that and you can see it later. So you cannot, basically all you can do is just discard this term to get the derivative, but f prime of x is never equal to the left-hand side unless f is a linear function, unless this f is a linear function, in which case it's just rise over run, right, a straight line. But in the new calculus, this is always true, okay? And why is this always true? Because this term here is always 0, so this here is the same as this, okay? That's all there is to it. So the new calculus is solid, and you can read about it in an introduction to new calculus. It takes a little more effort because it's 100% sound knowledge based on geometry, as is the Holy Grail of calculus, but the Holy Grail of calculus uses Newton's stupid ideas of a non-parallel secant line to a tangent. The new calculus solved the problem by using a parallel secant line to the tangent, okay? And of course, anybody who tells you, oh, you can't always find q of xh, he's just a crank like that Marcus Cliver. It doesn't matter whether it's a polynomial or an exponential or a trigonometric. This function, this theorem works for any smooth function. And yes, if you don't have a smooth function, you can just throw calculus out of the window, okay? You need a smooth function for this identity to be true. It's not true under any other situation. And now, so what was I saying earlier here? I was telling you that, do I have a pen here? My word, I don't see a pen. Where's that? No pen? Oh, this is an old version. Pen here? Okay, so pen. So like I said, if we calculate, we can't really do this by taking an infinite sum and dividing it by the interval width, right? We can't really do that. But the mean value theorem tells us that if we've got f and f prime, then the level magnitude of all these is simply f of x plus h minus f of x over h, okay? And if we want to get the area, we just multiply it by h. And this, of course, is equal to the integral from x to x plus h of f prime of x dx. And you'll notice that the idiots of mainstream academia have never understood this, because whenever they write this, they tend to change this to F, capital F, and you don't see immediately the relation, and this to just F. So you don't see immediately the relation between F and little f. And then there must be a relation. Otherwise, you cannot use this fundamental theorem of calculus, which comes from the mean value theorem. So I hope that, oh, by the way, over here, also in this applet shows you how if you change the area, then you simply, what you're doing is just squashing this area here, over here. Oops, get a pen again. Yeah, squashing this area into this section here so that you get a nice rectangle. Okay, and of course, if you move that anywhere else, if you move it over here, again, same thing. You put these two areas, these two gray areas, into the middle here, and you get a nice rectangle, and you can find the area under the curve. Okay, so that is all explained over here. You can define the derivative in terms of this historic geometric identity, which comes from the historic geometric theorem, which is proved in my article on the geometric theorem, and also the definite integral, which is simply the area under the curve, under this curve here, is simply h times the level magnitude, which is this expression here. Okay, this is the level magnitude, which, as we decided early on, we're going to give new names, right? We're going to call levelmag in English, flaggig in German, and whatever else. Okay, so that's pretty much it. I hope you've enjoyed this, and I hope you've actually managed to take a lot away from it. I will put a link to all the appropriate articles in here so that you can study them further. My name is John Gabriel. This is a New Calculus channel. Goodbye.